So, we will continue the same topic, that is the linear functionals on a finite dimensional case first, and here we will find out what is the dual basis for x, where x is our norm space, norm space, and the dimension is finite dimensional norm space with dimension n. Okay. So, dimension of this norm space is n, and let E1 E2 En, these are the bases of x, basis of x. As we know that all the linear functional, set of all linear functionals defined on x, this we denoted by x star, and in fact, it forms a vector space under the suitable addition and scalar multiplication. This we have discussed. So, suppose f is f is an element of say x star, f is an element of this x star, that is a linear functional, defined on x, a linear function defined on x. Any element x belonging to capital X can be expressed as in terms of this basis element xi k eta xi k e k, where E1 E2 En are the basis for x. F is a linear functional defined on it. So, f of x, this will be equal to sigma k equal to 1 to n xi k f of E k. Okay. Now, f is a functional. So, f of E k will be have some scalar value. So, let it be this equal to sigma xi k alpha k, k is 1 to n, where alpha k is the value of the E k under f. Okay. This much we can say.
So, E k is the vector.
E k, these are the basis element, where E k is r, these are the basis element, basis for x. Okay. So, alpha k is the value of the function at the point E k. Now, if we look the equation this say 1, then f can be uniquely determined by the values of alpha k at the n basis element. So, we can say from here and alpha, so f is uniquely determined by its values alpha k at the n basis vectors E1, E2, En of x. Is it clear? It means, if these alpha 1, alpha 2, alpha n are given, okay, or the values are E1, E2, Ens are known, because it is a basis for this. So, any x can be expressed uniquely this representation is unique, Therefore, the value of f will also be unique, and it will depends on alpha k, the value of f k, okay, uniquely determined by. If I think a converse direction, suppose alpha 1, alpha 2, alpha n are given, then also we can find the f, clear. So, for any choice of alpha 1, alpha 2, alpha n, one can obtain f. So, let us take the particular case of alpha 1, alpha 2. So, conversely, every n tuples of scalars alpha 1, alpha 2, alpha n determines a linear functional, determines a linear functional on x by the equation 1, is it not, by 1, because this is the equation 1, and here if we know alpha 1, alpha 2, alpha n, then we can. So, in particular, let us take this way. In particular, suppose I take this scalars 1, 0, 0, 0. It means this is one set of scalars, that is, this is alpha 1, this is alpha 2, and this is alpha n. Okay. We can get similarly, if we take this scalars, what will be the our f of x? F of x becomes sigma xi k equal to 1 to n, and alpha k will be this, okay, alpha k, where alpha k is 0 when k is equal to k is not equal to 1, and 1 when k is equal to 1 in this case. So, basically this is nothing but what, xi 1, and this is equal to f 1 x. Let it be denote this by, is it okay? Similarly, if suppose I take another set of scalar 0, 1, 0, 0, 0, then correspondingly we get f 2 x as xi 2 and continue this. So, we get from 0, 0, 0, 1 the corresponding n x will be xi n. Is it okay? It means this set of values. So, this set of scalars. So, we get so these scalars gives linear functionals f 1, f 2, f n, okay, f 1, f 2, f n with the values like this, that f j E k is nothing but the canonical delta j k, which is equal to 0 and 1 if j is not equal to k and j equal to k, is it not? When we say f j e k, when f 1 means this, okay, 1 alpha 1. So, it is equal to 1, otherwise 0. So, this will give the corresponding. It means, when even E2 Ens are given, we can construct this f 1, f 2, f n with the help of this scalars. Okay. Now, this set of linear functionals, that is this set f 1, f 2, f n, satisfying that condition f j E k is the canonical delta j k, is known as the basis or dual basis of the basis E1, E2, En. Is it okay? So, this is the dual basis of it. But why it is known as the basis? Because basis means it should be linearly independent and it should span the whole class. Okay? So, dual basis of this. So, in fact, we will show this is why. The question is why. Okay? It means unless we prove that this collection F1, F2, Fn is a linearly independent set and it spans any linear functional, then only it will be the basis for x star. So, we do this in the form of this theorem. What this theorem says, that let x be an n dimensional, let x be an n dimensional vector space and E, which is E1, E2, En, and E, which is E1, E2, En, a basis for x. Okay. Then we claim that collection of these element F1, F2, Fn, say capital F, this set given by this way, Fj Ek is the canonical delta delta Jk, which is equal to 0 and 1 when j is not equal to k and 1 when j is equal to k. Given by this is a basis for the algebraic dual x star of x. And not only this, the dimension of x star will be the same as dimension of x. Okay. So, this is true in case of finite dimension. If x be a finite dimensional space, then we can find out the algebraic dual for it, and the dimension of x star and dimension of x will be same. Let us see the proof. So, we wanted to show that this class F is a basis for a dual x star. It means x star is the set of linear functional. So, this set must be linearly independent and it should span x star. So, first is F is linearly independent. This we wanted to show. So, let us consider this expression sigma beta k f k x equal to 0, k equal to 1 to n, where beta and beta k are scalars, okay, and f k 1, f k 2 etc. defined like this, and x is element of x is an element of capital X. Okay. Now, since x is an element of x, so x can choose any value E1, E2, En, these are the basis element of x. So, x can take E1, E2 etc. So, put x, replace x by x, replace x by Ej, which is also an element of x. So, what it gives? So, we get from here is that sigma k equal to 1 to n beta k f k E j equal to 0. This will implies that beta j must be 0, because f k E j will be 1 and rest will be 0, canonical delta. So, okay, because f k E j is satisfying this condition, f k E j is delta j k. So, it is 1 otherwise it is 0. So, beta j is 0. It means that if I keep on replacing x by e 1, e 2, e n, then all these coefficient beta 1, beta 2, beta n are coming to be 0. Is it okay?
So, you k equal to j?
K is equal to 1 to n. So, when you take here f k e j, when k equal to j, it is 1, otherwise 0. So, it will be equal to beta j or beta k? Any. Okay? Beta k or beta j. When k is equal to j, this is 0. Okay? Otherwise, it is 0. So, beta k. So, so we say all beta k will be 0 for all k, 1 to n. Therefore, this set f 1, f 2, f n is linearly independent.
So, beta k will be 0 provided, sir, it is not equal to, k is not equal to j. If k equal to j, then it will not be equal to 0.
No. If there are two, this case, how will you, suppose I expand this thing, okay? What you get it, or let it be expand this one, beta 1 f k e 1, no, f 1 e j, then beta 2 f 2 e j, like this, beta j f j e j, and so on, like this. So, it will be beta j. Okay. So, now this part will be 0, this part will be 0, only this part will be 1. So, only beta j will be left out and rest will be, so beta j will be 0, because this is equal to 0, total sum is 0, but here only one part is left. So, beta j will be 0. It means that beta k will be 0 for all k, similar. So, this is linearly independent. Is it okay? Now, next to show that L of f is x star, that is the set f, f spans x star. Means if we take any arbitrary element of x star, that can be expressed as a linear combination of the elements of f. Okay. So, let us take any f. So, take f belongs to x star. Clear? Okay. So, and x, which is sigma x I k e k, k is 1 to n, is an element of x. So, f of x will be equal to what? Sigma x I k, k equal to 1 to n, and f of e k. Is it okay or not? F of e k. Now, let it be this one equation. Okay, let it be 2. Okay. Now, we know that f j x, what is f j x? F j sigma x I k e k, k equal to 1 to n, okay, which is equal to sigma k equal to 1 to n x I k f j e k, because f is linear. Now, f j e k is canonical delta. So, when j is equal to k, it is 1, otherwise 0. So, basically this is equal to what? X I j. Is it okay or not? Clear? Again, in a similar way, this rest of the part will be 0 and only one term will be left, which is x I j. So, x I j can be replaced by f j x. Okay. So, in equation 2, if I take f x sigma k equal to 1 to n, x I k, can you not write this f k x? Okay. And this f of e k is nothing but a constant alpha k. scalar quantity. Clear? So, what you can get it that f can be expressed as linear combination of the element of f k, a linear combination of f 1, f 2, f n. Clear? Therefore, f is a basis for, therefore, f is a basis. Is it clear? So, now it's now this result, not only this, once it is basis, so any element f can be expressed as a linear combination of f 1, f 2, f n, and these are the bases. So, dimension of this will be n, only n terms. So, x star and dimension of x will be the identical. Clear? So, that proves this. I think it is okay. Now, we have a very interesting result that is in the form of lemma. What this says? Let x be a finite dimensional vector space if x naught belongs to capital X. If x naught belongs to capital X, has the property that f of x naught is 0 for all f belonging to x star, then x naught must be 0. Then x naught must be 0. So, what is this property? Suppose x be a finite dimensional vector space and x naught be an arbitrary point on it. If the image of this point under f is 0 for all linear functional defined on x, then this is only possible when the point x naught must be 0. Means there is no non-zero point whose image will always be 0 for all f linear functional. It is not possible. Only possible is that if f is a 0 functional, then image of any element will be 0, but here x is fixed, point is fixed. We are choosing the images under different f. So, there is a possibility that few images may go to 0, but all these for all such f, if it is 0, it means the point x naught has to be 0. So, that is the result. Is it clear? The proof is again simple. Dimension of x is given dimension of x say n, okay, and E1, E2, En be the basis for x. So, x can be let and x naught is a point in x. So, x naught can be expressed as a linear combination of these basis element. So, we can write as xi naught j e j. Why not? Because of this 0, okay, and j is equal to 1 to n. Okay. Now, f is linear function, f belongs to x star. So, f of x naught, this will be equal to sigma j equal to 1 to n xi naught j and f of e j, but f of e j is alpha j, which is j equal to 1 to n xi naught j and alpha j. Now, as we have discussed already, if E1, E2, n are given, then f can be uniquely determined by its value at this point, or if alpha 1, alpha 2, alpha n are known, then one can identify f, one can get the value of f. So, for each f means if we keep on changing alpha j, this will correspondingly for any f belongs to x naught, for any f belongs to x star. So, if this is true for every f belongs to x star, this is also true for every sequence of scalars alpha j. You follow me? F determines alpha j. So, when you change f, alpha j will change, okay? But f is any arbitrary f. So, it means you are getting a plenty numbers of alpha j. So, if we say that this result is, say, keep on changing alpha j, if this is true for this all alphas, okay. Now, what is given is that this f of x naught is 0 for all f belongs to x star. This is given. It means that is sigma of xi naught j, j equal to 1 to n, e alpha j equal to 0 is given for all alpha j. Is it not? For any f means for all alphas also. Okay? For any alpha you put. So, if a linear expression is 0 for any values of alpha j, this is only possible when xi naught j must be 0. So, this implies that xi naught j must be 0 for j equal to, otherwise it is not possible. This combination total sum cannot be 0 for any change of alpha j, alpha 1, alpha 2, alpha n. Okay? So, this is only, this implies our x naught will be 0, and that completes the result. Okay? I think it is okay. Yes, okay.
This is from the first equation.
From the first equation. Okay. This is
As xi 0 j is 0 for all j, so the x 0
earlier one.
Earlier one, that will be 0.
Okay. So, okay. Clear? So, that's good. So, this is another. Now, interesting is that in case of the finite dimensional, a finite dimensional vector space, a finite dimensional vector space is algebraically reflexive. A finite dimensional vector space is algebraically reflexive. It means, if the second dual of this coincide with itself, or if there is a mapping, canonical mapping from x to x double star, which is 1 1 on 2 and preserve all the operation, and then images will be the identical, then we say it is a reflexive mapping. So, okay. So, in case of the finite dimensional, if x be a finite dimensional vector space, then it should be a reflexive space. Okay. We know that a mapping C from x to x double star, which transfer x to g of x, such that C x f equal to C x f equal to g of x f equal to f x. Is it not? That way we have defined. Canonical embedding is a canonical embedding, this we know, is it not? So, if we take C x naught and it is 1 1 mapping, and R C is a subset of this, okay? Canonical embedding from x to x double star, from x to x double star. This we had discussed. Now, if C of x naught f is 0, means C of x naught f is 0 for all f, belongs to x star. Clear? So, this implies that g of x naught f, which is equal to f x naught, is 0 for all f belongs to x star. But we have seen that f of x naught is 0 for all f implies x naught must be 0. Okay? So, if C x naught is 0 means C x naught f is 0, it means for all f this is true. So, f of x naught 0. So, C x naught equal to 0 implies x naught is 0. So, therefore, C inverse exists. That result is okay. C inverse will exist. Once C inverse exists, C inverse is a mapping from the range set of C to x, range set C to x. And not only this, when it exists, so we get from here the dimension of R C is the same as dimension of x. As soon as inverse exists, both will have the same dimension. But yeah. But if even E2 is a finite dimensional case, so in case of the finite dimensional, dimension of x and x double star is the same. So, since x is finite dimensional, dimension of this equal to dimension of x, which is equal to dimension of x double star, as x is finite dimensional vector space. So, once it is finite dimensional vector space, this will also be true. Dimension of x equal to dimension R C. Therefore, from here dimension of R C is the same as dimension of star. Clear? So, this shows that the C, which is a mapping from x to x double star, is a 1/1 mapping, and it preserves the operation as well as dimension of R C and dimension of x star is the same, which is the same as the dimension of x. Okay. So, this shows that our space is finite dimensional space is reflexive. Okay. So, this shows the reflexive.
So, x is reflexive.
X is reflexive. X is reflexive. I think it's okay. Now, so far we have seen the linear functional on the finite dimensional case. Now, we are switching off to a arbitrary case in finite dimensional norm space. So, let x and y be any infinite dimensional space be a norm spaces, need not be a finite dimensional, okay, over the same field. Over the same field. B denote B x y, B denote B x y as the set of all bounded linear operators, from x to y, boundary linear operator from x to y. Now, this B x y forms a vector space under the operations T1 plus T2x is T1x plus T2x, and alpha times Tx equal to alpha of Tx. Okay? That usual, just like a linear functional. Similarly, here the operators. So, in a similar way we can show this is a, and it is a norm space, and it forms norm space under the norm defined as norm of T equal to supremum norm of Tx over norm x. X belongs to the domain of T where x is not equal to 0. Okay? Under this norm, it will be not, we can prove this is a norm. Clear? And this same definition, if you remember, this is also equivalent to say supremum of norm Tx where x belongs to dt and norm of x is 1. Both are equivalent definition. So, this gives you the norm. It means Bx by becomes a norm under this. Now, let me just clarify one thing. This is the norm on Bx by. So, we can say it is the norm of T is on Bx by. Okay? This is the norm on y. This is the norm on x. But writing always this way is a very clumsy. So, we try to avoid it, but understanding is whenever the Tx is given, it means it is the point in y. So, the norm of y is used, here the norm of x is used, and this is the norm of the operator from x to y, a bounded linear operator from x to y. Is clear? Now, question arises, under what condition this Bx by becomes a Banach space? Because it is a norm space, we can prove all the condition of norms are satisfied. So, Bx by is a norm space, fine, Bx by is a norm, but whether it is a Banach space or not, and what should be the restriction on x and y, so that Bx by under the same norm becomes a Banach, that is a complete norm space. So, we will show that when y is Banach, then Bx by is a Banach space. So, if capital Y is a Banach space, then the set of linear operator from x to y is a Banach space under the same norm 1, under this norm say 3, okay, under 3. Okay, under the norm 3. So, what is required to show here? If y is a Banach, means you have to choose Bx by, you want it to be a Banach. So, it means you consider a Cauchy sequence of the operators, boundary linear operator on Bx by, and if that Cauchy sequence converges to an operator which is also bounded and linear, and convergence is in the norm of Bx by, then it is a complete norm space. So, let us choose T n be an Cauchy sequence of bounded linear operators of Vx by, of bounded linear operators in Vx by. Okay. Bounded linear operator in Vx by. So, T n is Cauchy means, so for given epsilon greater than 0, there exists an capital N depending on epsilon such that norm of T n minus norm of T m minus T m, this will be less than epsilon for n m greater than equal to capital N by definition. Clear? So, consider now norm of T n x minus T m x, where x belongs to capital X. Consider this. This can be written as norm of T n minus T m x. Now, T n is a sequence of bounded linear operator. So, T n minus T m will also be bounded linear operator. So, it will be less than equal to norm of T n minus T m into norm of x. Okay. But as n m goes to infinity, the norm of T n minus T m goes to 0. So, basically this is less than equal to say epsilon 1 into norm x for n m greater than equal to capital N. Okay. Is it okay now? So, suppose I fixed x. Once you fix x, this quantity is fixed. So, we can write epsilon 1 into norm x as epsilon 2. So, T n x minus T m x is less than epsilon 2 for n m greater than equal to n. It means for fixed x, this sequence T n x behaves as a Cauchy sequence in y. Is it not? Because T n x is the image of x under T n. So, it is a point of y, and difference, any arbitrary difference is less than epsilon. Therefore, for fixed x, it is a Cauchy sequence in y, but y is complete. But y is complete. But y is a complete norm space, because it is Banach. So, every Cauchy sequence must be convergent. So, this Cauchy sequence, this noted. Okay. So, the sequence T n x will converge to a point y in capital Y. Is it okay or not? As n tends to, this sequence will converge to a. So, now what we get? So, it means that is this is our x, this is our y. Okay. T is an this is an operator T n. Now, here you are taking x. So, image of this T n x is coming to be y. When n tends to, this is equal to T n x. So, this image is going to y as n tends to infinity. Is it not? Do you follow me? It means that this y is obtained because of x fixed. So, there must be an operator which relates directly to x to y. Okay. So, there exists an operator T which transfer from x to y such that T of x equal to y. Is it clear? By
The meaning is that T n x
हाँ,
is converting to y
हाँ,
as n tends to infinity.
as n tends to infinity.
Means we are taking so many operators and we are
हाँ,
getting
yeah,
so
limiting of these values
Yeah.
T1, T2, Tn, this x is coming to be y.
y. So,
So, it means there must be an operator which can transfer x directly to y. So, an operator exists T and y. Now, this operator, it may not be bounded, may not be linear, is it not? So, we have to show if it is bounded and linear, then only it will belongs to the class Bxy. Clear? So, now to show T is linear, and up to here we have shown the existence of T. This shows the existence of an operator T from x to y. This is the only thing we have shown so far. Now, if I further prove that T is linear as well as bounded, then it must be a point in Bxy. Now, T is linear can be proved like this: limit of this T n alpha x plus beta y as n tends to infinity. Now, since T n is linear, so because of the property of the linearity, this can go alpha T n x plus beta T n y. because t is linear, Tn is linear. Okay. And then limit, when you take the limit here, so finally you get alpha T x plus beta T y, because limit of Tn is T y, is it not? We are identifying limiting of Tn is T y. So, here is also T of, this can also be written as T of alpha x plus beta y. Is it okay or not? Because limiting value of Tn we are denoting by T. So, basically T satisfies this condition. So, T is linear. Okay. Is it clear? Now, T is bounded. Okay. This I will do it from here, since norm of Tn x minus Tm x is less than or equal to epsilon 1 into norm x. This we have shown. Okay. So, now let us take fix x and let m tends to infinity. So, if m tends to infinity, then this implies Tn x minus Tx will tends to 0, is it not? No, sorry, this is less than or equal to, I am sorry, this is less than or equal to epsilon 1 into norm x. Okay. Norm x, is it correct or not? By this only m tends to infinity, limit is a continuous function. So, it will go inside, this will not be affected, it will affect, this Tm will go to T. So, as n tends to infinity, okay, like this. Now, from here can you say Tn minus Tx is less than or equal to some epsilon 1 norm x for n greater than or equal to capital N. Is it okay? Now, this shows.
Sir, here let n turns to infinity.
No, here fix n,
Fix x.
n and x both, okay, and m tends to infinity. Then only fix fix x, okay, fix x and m tends to infinity. This I am not touching. So, here you can say n is greater than or equal to capital N. Is okay now? Okay. Now, this is, so can you say this sequence Tn minus T, this is a bounded operator by definition? Okay, norm x, okay, so some constant. So, it is a bounded operator. So, once it is a bounded operator, then you can say therefore, T which can be expressed as Tn minus T is a bounded operator. Okay. This is bounded linear operator, because this is bounded linear, this is bounded linear. So, combination of the two bounded linear operator. So, T will be bounded linear operator. Okay. Is it clear or not? So, T is not only linear, it is also bounded. Now, further norm of Tn minus T x, this is less than or equal to epsilon times norm x. So, from here we get norm of Tn minus T.
So, this point is not clear.
Which one?
T is a bounded linear operator.
Tn minus T we have shown bounded. Tn is also given to be bounded. So, two operator is the sum of the bounded operator are bounded.
Tn is bounded.
It is given. Tn is the element of Bxy. So, it is bounded linear operator. So, these two are bounded linear, therefore, T is bounded linear. Now, this will be equal to, if I norm of Tn x, what is the norm of Tn x? This is the supremum, take the supremum over all x. So, it is bounded. Okay. So, we get the supremum of norm of Tn x is finite. Take this norm of, I think I will just write, okay, this is divided by norm x, take supremum over x. Is it not less than this? Okay, which is equal to norm of T n minus T, as n greater than equal to capital N.
Sir, we are taking supremum
over x. Over x.
As this condition is valid for all x.
For all x. Supremum is taken for all x. Okay. And this is true for n greater than equal to n. So, this is also true for n greater. Therefore, T n converges to T in the norm of B x y, because norm of T n minus T goes to 0. So, this completes the proof that
T n minus T, it is equal to supremum over x of this.
supremum of this divided by x. You divide this by x. So, norm of T n minus T x over norm x, supremum is taken over x. Now, this is less than equal to epsilon when n is greater than equal to n.
So, this is by definition.
By definition. Which one? This equal to this by definition, because norm of T is the supremum norm T x over norm x. So, by definition. So, this is equal to this, which is less than. So, this shows when n is sufficiently large, T n will go to T. Therefore, T n converges in the norm of this. Okay? Clear? So, this completes the proof. Now, so this is complete. Now, as particular case, if I take the functional A, a bounded linear functional on a norm space X is a bounded linear operator from x to y, where y is either R or C. A bounded linear functional is a bounded linear operator, where the range set becomes the field of scalar either R or C. So, basically f is a mapping from x, R or C. This is a bounded linear functional. Okay? Bounded linear functional. So, bounded linear functional is a particular case of the bounded linear operator, where the domain remains the same, range becomes either R or C, but R and C are complete. Okay. Now, this is be denoted by, so B x R or C, this be denoted by x dash, set of all bounded linear functionals on X be denoted by x dash and is called dual space of X. Okay? It is called the dual space of X. Is this clear? Denoted by x dash. So, first we have defined the bounded linear operator, then replacing by R or C, we are getting a bounded linear functional, and that collection is called the dual space, and it will be complete because R and C will always be complete. Okay? So, in the next class we will see the examples of the dual spaces. Okay? Thank you.